everyone. So in this little lecture, we're going to talk about work done by variable forces. So we know that equation that we've learned for work previously, force times displacement times the cosine of theta, we can only use that equation if we have a constant force. So in this case, we do not have a constant force. So if we consider a force in the positive direction of the x-axis, whose magnitude varies with position x, as we can see here, the magnitude of the force is varying as our position changes, then we can't use that equation because the force is not constant, like I said before. So instead, we're going to integrate, and work is the area under the curve. Now, just a side note here, I know that we integrate a lot in this AP Physics C class, and we also take the derivative a lot. So what you want to do here to remember whether you integrate or you take the derivative, I just want you to look at this graph right here, okay? So if we're taking the integral, that means we're getting the area under the curve, and I'm going to go through the steps on the next slide here to explain why that is, just give you a little refresher, okay? But remember, if we're taking the area, it's going to be base times height, and base here is our displacement, height is force. So we get force times displacement, and that, again, is the work equation. Force times displacement, of course, times the cosine of theta. But that will remind you that, okay, the work is going to be the area under the curve, the work done. And because of it's the area under the curve, then you're integrating this function to find work. Now, on the other hand, derivatives, remember, it's the slope of the curve. So if we looked at the slope of this curve, rise over run, force over displacement, that doesn't really give us anything, okay? We don't know anything that's equal to force divided by displacement. So we're not looking at the slope here or the derivative. We want to integrate to find the area under the curve in order to get work. Now, when we integrate to find work, again, I'm just going to go through the steps of integration and kind of try to explain why exactly we want to integrate and how integration works. So what you're going to do is when you're integrating, you're dividing that area under the curve into a number of narrow strips with width delta x. So we can see that these are our narrow strips here. And because they're so narrow, it's going to permit us to take the force during that displacement delta x as being reasonably constant over that interval, not integral, over that interval. So F sub j average is going to be the average value of that force over that interval. And that's going to be the height of whatever strip we're talking about. Okay, so it's our average force and the height of that strip. So if that's considered constant, the increment work done in that interval is just that force times the displacement. Because remember, again, we're taking the area, and that's just going to be, base times height, height times base. So we end up getting force times displacement of every single one of those strips right there. So it's the area of the rectangle there. Now, of course, we have a bunch of little tiny rectangles. So what we're going to do is we want to add up each of those areas from x initial to x final. So that notation is written as sum notation. So the total work done is equal to the sum of those, the area of each of those strips, right? So you get the sum of each F sub j average times your delta x. And then by using that limit, we're going to reduce that strip width to approach 0 to make our approximation better, because the smaller our width of each strip is, the more approximate our average force is to the exact force at that specific point, that specific displacement. So using the limit function here, we can then reduce our delta x's down to 0, and we get a more approximate, a more exact approximation here. Now, of course, we can then just rewrite this as the integral. So the limit, remember, is the integral of the function f of x, so the force as it changes with position, between the limits of the final position minus the initial position. So this is what we get, and this is why we integrate. So that's just a little, we've gone through this before, but again, just kind of how and why we integrate in order to find the work here. Now, if we have 3 dimensions, So say we have a force equation in the x direction. So as the force changes with respect to our displacement in the x direction, an equation as the force changes in the y direction, and as the force changes in the z direction. So the components f sub x, f sub y, and f sub z depend on the position of the particle. So those forces are functions of the position of that particle. So 3 simplifications that we make here are that f sub x only depends on x and not y and z, f sub y only depends on y, and f sub z only depends on z. So the particle moves through this incremental displacement, dr equals dx I hat plus dy j hat plus dz k hat, and that increment work w is done on the particle f during displacement dr. So here's our increment work done. That's equal to the force times that increment displacement. Now, this is all just a fancy way of saying if you have a function in the x, y, z direction of force as it changes with position, you're just going to do the same thing. You're going to take the integral in order to find work. All right. So this slide is just mumbo jumbo saying you're going to do this if you have a function of f, the force as it changes in the x direction, the y direction, the z direction. So the net work done by the force while the particle moves from an initial position r sub I having coordinates x initial, y initial, z initial to a final r vector final having coordinates x final, y final, z final is just this right here. So again, if you get a function of the force as it changes with our x position, a function of the force as it changes with our y position, and a function of the force as it changes with the z position, you're just going to take the integral of each as that position changes and then add them up together like we have done before.